Okay, 1-4, number 2. Let's look more at discontinuities. So we looked at the definition of continuity at a specific point. Function exists, limit must exist, and furthermore, the value of the function and the limit of the function have to be the same number. If a function has a discontinuity, it's going to occur at a domain restriction. So that's why understanding how to find the domain of a function and being able to do it are paramount to understanding discontinuities. Right, so if a discontinuity occurs, it's going to occur at a domain restriction. So the first thing we do, we determine the domain. There are two types of discontinuities, and you studied these last year. Removable versus non-removable discontinuities. Graphically, when we look at when we see a removable discontinuity, it's going to be a hole on the graph. A non-removable discontinuity graphically can be a jump, a vertical asymptote, and it can be a hole as well. What separates the two is the existence of a limit. If the limit exists, then the discontinuity is described as removable. If the limit does not exist, then we would describe the discontinuity as non-removable. So let's go backwards real quickly. We said that this function here was discontinuous because the value of the function and the limit of the function didn't exist. The discontinuity, however, we would describe as removable because we weren't able to find a limit. On the second example, the value of the function didn't exist, that's why it couldn't be continuous, but when we look at the limit from the left and the right approach the same y value, so we would categorize this one as removable as well. For the third example, we determined that the limit of the function did not exist, so we would categorize that as a non-removable discontinuity. Okay, so let's look at some examples of that. For each of the following, determine if any discontinuities occur. If they do, identify them as removable or non-removable. Piecewise functions get tricky. So the only place that we're looking at is at x is equal to 1. Does a discontinuity occur where the graph of the functions change from the quadratic to the line? So let's look at our three cases. Does f of 1 exist? Well, the function is quadratic, so the value of the function is 1. Now we need to look at the limit of the function. Well, in order to do that, we need one-sided limits, because on either side of the function, two different graphs are shown. As x approaches 1 on the right-hand side, so numbers bigger than 1, we're looking at the graph of the quadratic. As x approaches 1 from the left-hand side, so values less than 1, the graph would be the line. So making a direct substitution, to the quadratic I get 1, and to the line I get 1. Since the one-sided limits are equal, it tells us that the limit is equal to 1 as well. Since those values are the same number, then the function is continuous. So at x is equal to 1, no discontinuity. Continuous for all real numbers. Okay, another piecewise example. When I look at each of these functions individually, quadratic, line, and quadratic, their domains are all real numbers. So the only place that a discontinuity could occur is at the domain switches from one piece to the other. So we're going to have to look at x is equal to 1 and x is equal to 2. X is greater than 2. Sorry about that. Alright, so x is equal to 1. the function exists. To find f of 1 is equal to 1, I look at the line. So f of 1 is equal to 9. To investigate the limit, we look from the left of 1 and from the right of 1. For all values less than 1, it's the quadratic x squared. For all values to the right of 1, it's the line 10 minus x. So looking at a direct substitution, I get 1 and 9. Since the one-sided limits are not equal, the limit as x approaches 1 does not exist. If one of the conditions is not met, then at x is equal to 1, we have a discontinuity. Now to determine if it's removable or non-removable, we look specifically at the limit. Since the limit does not exist, it's a non-removable discontinuity. Alright, at x is equal to 2. Let's make this x is bigger than or equal to 2 because we need the function equal somewhere. When x is equal to 2, I plug into the quadratic. 6 times 2 minus 2 squared. 12 minus 4 gives us a y value of 8. Now for the limit, we look at the one-sided limits. X approaches 2 from the left-hand side. From the left-hand side is the line 10 minus x. From the right-hand side of 2, it's the quadratic 6x minus x squared. So making direct substitutions into each of these, 10 minus 2 would give us 8. 12 minus 4 would give us 8. So it shows us that the limit does exist, and the limit is equal to 8. So f of c and the limit as x approaches c are the same value. Therefore, the function is continuous at x is equal to 2. Okay, so the directions, remember, are determine if any discontinuities occur. The only possibility discontinuity could occur is at a domain restriction. This function I'm dividing by x, so my domain is that x cannot equal 0. Because there's a domain restriction, I know that a discontinuity is going to occur. It's up to you to determine what type of discontinuity it is. Alright, so let's look at the limit. The limit as x approaches 0 from the left. The limit as x approaches 0 from the right. Alright, we go back into the absolute value of x. If x is a positive number, the absolute value doesn't do anything to the number on the inside of the bars. If x is a negative number, then the absolute value takes the opposite of that negative number in order to make it positive. So as x approaches 0 from the left-hand side, my numerator stays the same, and my denominator is actually equal to negative x. So the limit as x approaches 0 from the left would give me a value of negative 1. The limit as x approaches 0 from the right-hand side, any number greater than 0, the absolute value doesn't affect. So the absolute value is equal to positive x. The limit does not exist because the one-sided limits are not the same value. Therefore, my discontinuity is non-removable. Where does it occur? It occurs at the domain restriction of x is equal to 0. Okay, so for this one, I know there's going to be a domain restriction because it's a rational function. So let's factor the bottom. Negative 10 that adds negative 3. Negative 5 times 2 is negative 10. Negative 5 plus 2 is negative 3. So x can equal 5. X can equal negative 2. So let's look at each of those cases. Before we do that, though, I'm going to attempt to simplify my function. Now that it's in factored form, these cancel. So when we discuss the limits, we're going to use the simplified function to determine the limits. Limit as x approaches negative 2 of my simplified function gives me 1 over negative 7. Since the limit exists, it would be a removable discontinuity at x is equal to negative 2. When I look at the limit as x approaches 5 of my simplified function, I get number over 0. Okay? Number over 0 is a very specific answer, and it tells us that the limit does not exist. The limit does not exist at 5, therefore it would be a non-removable at x is equal to 5. So I don't need my one-sided limits if a direct substitution gives me an answer. Okay? If I look at example 3, direct substitution gives us 0 over 0. So we can't use direct substitution because it gives us an indeterminate form. In example 4, when we simplified the function, we can make direct substitutions and we get valid answers for our limit statements. Plus 3. If I look at the domain, I know that x has to be bigger than or equal to negative 3. Okay, we can't take the square root of a negative, so solving that simple inequality. In our interval notation, it would be hard bracket at negative 3 to positive infinity. On this domain, okay, so discontinuity occurs at a domain restriction. Well, we determine what the domain is, but any number bigger than negative 3 in the function. So we would say f of x here is continuous on its entire domain. So no discontinuities occur. Okay, lastly, f of x is x plus sine of x. Only place a domain or discontinuity would occur is at a domain restriction. Domain of x, line, all reals. Sine of x, all reals. Domain is all real numbers. So we would say our function is continuous on the entire number line. Alright, and the last thing for this lesson, the intermediate value theorem. I just want you to copy this slide down if you didn't print it out, and we'll start here. Okay, leave space because I'm going to draw an example. The intermediate value theorem, if a function is continuous on a closed interval, and we have some y value between f of a and f of b, there exists at least one number, this is an x value, in the interval such that f of c equals k. Alright, so just copy this down and we'll discuss this in class in the interest of time.